So the problem we're going to do here is a titration problem. We are going to calculate the pH at the equivalence point, but this is not going to be an acid titrated with a base. Instead, we have 25 milliliters of a 0.1 molar NH3 solution that it's going to get titrated with HCl, which is a strong acid. So we are going to know, even before we do anything, that we have a weak base, strong acid titration. And so we know that the pH will, because it is a weak base, we would expect the pH at the equivalence point to be less than 7. So let's just review that real quickly. If I have a strong acid titrated with a strong base, that would end up at a pH of 7, because none of the products of the titration have any influence on pH, or the other way around. Doesn't matter whether I start with a strong acid or start with a strong base, I'm still going to end up with a pH of 7. But if I have a weak base, I would start with a pH that is above 7, the titration would be performed, and then we end up with a pH that is less than 7. So our first step here in any titration is you need to write the neutralization reaction. So it doesn't matter what your starting point is or what you're adding, you're going to write the neutralization reaction. So we start with, in the Erlenmeyer flask, ammonia. We add HCl to it. The products of that, you could write that as NH4Cl aqueous, but I'm going to write it as separate so that I can really envision what is going to end up in the beaker, which is ammonium ions. Now, ammonium is itself a weak acid. It is the conjugate acid of the weak base NH3. So if NH3 is a weak base, its conjugate acid is also a weak acid. And then I'm also going to get Cl minus. Now, Cl minus is the conjugate base of a strong acid, so it does nothing. There's no way that it could act as a base at all. Cl minus is not going to have any effect on the final pH. So our next step, we notice single arrow on the neutralization reaction. And again, we're kind of like artificially treating this as if this acts in, completely separate steps, even though really everything's going to be happening at the same time in the actual beaker. So our next step is stoichiometry. If I have, the thing we want to do for this is to think about which one of the substances, I have two substances, NH3 and HCl, which one of those substances do I know the most about? And if you look up at the starting information, I know both the volume and the concentration of NH3. That means I know everything about the NH3. So I'm going to start with the information about the NH3 that is something I could measure out in lab easily, and that would be volume. Volume is something I have graduated cylinder, I have a burette. That's easy to measure. So that's going to be my starting for my conversion factors. Convert that to liters. Now the key here is, especially for acids and bases, is the number, the unit, and the substance. So when I write 25 milliliters, I need to be really clear about 25 milliliters of what? I have 25 milliliters of NH3 solution, so I get that to liters, and then I'm going to write the concentration of 0.100 molar, capital M for molar. I'm going to write that as a conversion factor. So that means that if I had 1 liter, there would be 0.100 moles of NH3 in there, not capital M in that conversion factor. I only have 25 milliliters, so I have a whole lot less than 0.1 moles of NH3. So again, for the answer for that stoichiometry, number, unit, and substance. So not enough just to have a number. Now, kind of as an aside, but you're actually going to need this information in a bit, if the problem just asked you how much HCl would you have to add to get to the equivalence point, then you could do that pretty easily now. You could actually just add on one more conversion factor onto that, step above. Or I know that at equivalence point, the moles of acid equal moles of base. I have added the exact right number of moles of HCl to react with the exact right moles of NH3 that I had to start with. So if I had 0.0025 moles of NH3 in the beaker to start with, I would have to add 0.0025 moles of HCl to reach the equivalence point. Moles of acid equal moles of base. Now, then I just need to get to how am I adding those moles of HCl? I'm adding it in the form of a solution, so I have to take into account the concentration of the solution. I need moles to be on the bottom so they go away, and I'm going to end up with liters. And because the concentrations were the same, I end up with the same volume of HCl added that I had volume of NH3 solution in the beaker to start with. That's not always the case, right? If they weren't the same concentration, then they is not equal volume. So now that we know how much HCl I had to add, now we can we can apply that. We can do a before, add, after here. For again, I'm just rewriting the neutralization reaction. So what did I have in the beaker to start with? I had 2.5 times 10 to the negative 3 moles of NH3. I added 2.50 times 10 to the negative 3 moles of HCl. And then what do I have after that process? All the NH3 got used up. All the HCl got used up. That is the definition of the equivalence point. You added exactly as much HCl as you needed to add to react with all the NH3. What do I have after? Now, this last row is the important part. What do I have in the beaker when I have reached equivalence point? I have 2.50 times 10 to the negative 3 moles of NH4 plus, because every time I react, these are all 1-to-1 ratios, right, for the coefficients of the balanced chemical equation. So I have the NH4 plus that is the product of the reaction. In other words, when I neutralize NH3 with HCl, then H from the HCl goes on to the NH3 and I end up with NH4 plus. I've also created the same number of moles of Cl minus, but that does not affect pH. But they are there. Next step is, now that again, my envisioning of what do I have in my flask or my beaker is I have used up all the NH3, I have used up all the HCl that was added. I have a beaker that contains NH4 plus and Cl minus. Which one of those has an effect on pH? Well, only the NH4 plus, so I don't have to write the Cl minus. If I have NH4 in with water, which I do, then this equilibrium will be established, and NH3 is created, but it's not the NH3 that was in the beaker to start with. So even though there was an equilibrium in there to start with, we are just treating the beginning amount, the beginning situation as just NH3, which reacts with the HCl, and then we're going to say that's how much NH4 plus there is. Now figure out what the equilibrium situation is. In order to do the rest of my equilibrium, now equilibrium means rice, I need to know the initial concentration of NH4 plus. That's going to be moles per liter. I know how many moles I made, but now catch this. I have to figure out what is my new total volume. I had 25 milliliters of NH3 to start with, right? That was my beginning solution. I added 25 milliliters of HCl in order to reach the equivalence point, right? That was the previous calculation. How much do I have in there total? I now have 50 milliliters or 0.05 liters. So in other words, the volume changes when you add more stuff. When you add the HCl solution, the total volume changes. So now that I can put over there with my NH4 plus. The NH4 plus is the concentration that is there because of the equilibrium. The rice chart, we're just going to write regular old rice chart. And now NH4 plus is an acid, so I have to write a Ka expression for that, because NH4 plus is a very weak acid, but it is an acid. So I have to write that as a Ka that applies to that weak acid NH4 plus. Now I need to know what Ka is. Now normally, so I have two options for Ka. I can look it up in a table at the back of the book. If it's an exam, it could be listed in the exam or in a table of data available on an exam or a quiz. Or I can find it using the Kb for its associated base, which is what we're going to do in this case. Because normally a table in the back of the book or like the tabulated information isn't for NH4 plus, it's going to be for NH3, because NH3 is a very common weak base. So what we're going to use is the fact that Ka times Kb equals Kw. So the Ka would be for the conjugate acid of the weak base NH3. Now, Kb for NH3, we've used a bunch of times, 1.8 times 10 to the negative 5. You don't ever have to memorize those. That's tabulated information that would be made available. So Ka for NH4 plus times Kb for its linked base, right? Those go together. NH4 plus and NH3 are a conjugate acid and base pair. NH4 plus has a Ka, though, because it is a weak acid. Those are tied together by the autoionization of water. That's where that Kw comes from. And Kw for the autoionization of water, unless it's some other temperature, some other unique information, if it's just your normal 25 Celsius, is 1.0 times 10 to the negative 14. That means I can solve for Ka, and I get 5.6 times 10 to the negative 10. Check to make sure that makes sense. That is a very weak acid. That is definitely a weaker acid than NH3 is a weak base, right? NH3 is a weak base, but its K is a bigger number than the K for NH4+, indicating that NH4 plus is a pretty weak acid, which would make sense because the strength of acid-base pairs are tied together, again, because of equilibrium. Okay, so that means you can plug that number in over there for the Ka for NH4 plus and solve for X. You can definitely use the X is small approximation because that is an incredibly small K. And you get that's what X equals, 5.3 times 10 to the negative 6. Now go back in your Rice chart to see what does that X mean. That is the concentration of NH3, which I don't really care about. And more importantly for me, it is the concentration of the hydronium ion in that solution. Now, why is that hydronium there? Again, because NH4 plus was produced from the titration, from the neutralization reaction. It is itself a weak acid, so this equilibrium gets established. Once I have a concentration of H3O plus at equilibrium, I can find pH, and I get that the pH is 5.28, which is, as I expected, for a weak base, strong acid titration, it's going to be less than 7. Again, if I have a graph of that, I am going to be able to see that that would be the middle of the straight section, also sometimes called an inflection point. The middle of that straight section is where the pH at the equivalence point is, and as I would expect, it's less than 7.